Hi and welcome to this section where we're going to look continue our study of complex numbers, and for today we are going to look at Euler's formula. So they say in section 2.73, well, this is something else. There's this expression here. E to the x can be written in terms of these hyperbolic functions as hyperbolic cos of x plus the hyperbolic sine of x. Okay, so this links the exponential function and these hyperbolic functions here. So a similar and more important formula links the exponential and circular functions. So in here we have that e j theta is equal to cos theta plus j sine theta. Okay, and this is what we call Euler's formula. Okay, this justification, the justification for this definition depends on the following facts. We know that e j theta times e j theta 2, we know it's just, retain the power, we write the base and then we add the power here. So when expressed in terms of Euler's formula, this one here, so we see that it is going to become the cos of okay, maybe it's first, this is the direct, this is directly understood here because this is just theta 1 plus theta 2. So we have here theta 1 plus theta 2, then j theta 1 plus theta 2. Okay, this one here, direct as it is. However, we know that this here can be written as this here. Okay, this is the left hand side, this one here, because this is e j theta 1, this one, and then e times e j theta 2, which is exactly this one, and then the representation can be written as the one here on the right. Okay, and what do they say? It is similar, which is just 3.4 with R1 and R2. Okay, so you remember 3.4 where we said, do we have to go back? Okay, maybe. What was 3.4 telling us? 3.14, okay, I hope it's near here. 3.4, okay, 3.4, okay, 3.4, it was telling us that the product of z1 and z2, if you want to get the modulus of z1 and z2, you're simply going to get the modulus of r1 times the modulus of r2, okay? And the argument z1 and z2, you're just going to get the argument of z1 plus the argument of z2. So what they are trying to explain to us here is that you can see that we have z1, okay, we have z1 written in the exponential form and z2 written in the exponential form, and we can see that the product of these two, okay, is going to give us this, maybe let's call this one z1 z2, and we can see that for this the argument, okay, is just theta 1 plus theta 2. We are going to say the argument of z1 z2 is this angle here, okay, which is theta 1 plus theta 2, and then the modulus of z1 z2 is just r, which is 1. Okay, so they are saying r1 is 1, r2 is 1, so that is what we have here. And what else? If we are to divide, then we know we are just to rewrite this, and then we subtract theta 2 from theta 1. Okay, so this one here, the left hand side, is exactly this one here, because this is a j theta 1, this one here, in exponential form here, and then the denominator is just here. Okay, and then we have said we can write it directly as this, which is just this here, theta 1 minus theta 2 plus j sine theta 1 minus theta 2. So also we can see that the modulus is 1 and the argument is going to be theta 1 minus theta 2. Okay, even if you want to try this out another way by taking the complex conjugate, then you should be able to get to this one here. Okay, no need for that, we already have the result here. But even if you really want to work this one out by taking the complex conjugate and so on, multiplying numerator and denominator by the complex conjugate, you should be able to get the result we have here on the right hand side. So Euler's formula enables us to write the polar form of the complex number very precisely. So we have our complex number, and then we have its polar form, and then we have the Euler's formula here. We use Euler's formula, and then we write it in the exponential form here. Okay, r j r exponent j theta. Okay. So when they asked us to express the following numbers in exponential form, all you need to do is get the r and then get the theta. Okay, get the argument and then get the modulus. That's all. So here they compute the modulus, and then next they compute the argument, and then you can write it in form of r a j theta. Okay, and always remember to do the sketch, because the sketch will help us know where the angle is. For instance, this one here is just here, but then this, okay, and then this angle here is this one here, but then we can get it by saying we are going to get up to here, which is pi minus this angle, maybe we'll call it alpha. Okay, which they have here, they have pi minus then alpha. Alpha is tan inverse of 1 divided by 2. Okay, and then you write the same accordingly. Alright, as usual, it is always fun to write a few things here and there, find computational solutions, because that is the world we are living in right now. The theory helps us to understand, and then the heavy duty work will always carry out with the computational tools available to us. So you should be able to carry out with these computational tools. Maybe I can just show you just one. Let me just write this down somewhere. We have z1 is 1 plus j, and then z2 is root 3 plus j. And then they want us to determine the modulus of z1 and z2, or z1 divided by z2, and the argument of z1, z2, and so on and so on. Okay, so we do that. Okay, I'll clear my screen, and then I'll clear all the variables, and then I start. Maybe I can just hide that, so I can just use the command window. Okay, so as usual, we want to create these symbolic tools, z1 and z2. Okay, and then they say that z1 is 1 plus j, so we simply write it as 1 plus j. Okay, and then what is z2? Z2 is root 3. Root 3, how do they write root 3? There's a command, I think square root. Okay, square root of 3 plus j. Okay, it gives us that. And then next we want to find the modulus of z1, z2. We know that from here the modulus of z1, z2 is simply going to be the modulus of the modulus of z1 times z2, we have already seen, is simply going to be r1 times r2, and we see that z1 is 1 plus j, therefore r1 is simply the square root of 1 plus 1, the square root of x squared plus y squared. Okay, which is root of 2. And then z2, what is the modulus of z2? The modulus of z2 is going to be root 3 squared, which is 3 plus 1. Okay, square root of root 3 squared plus 1, which is square root of 4, which is 2. So we expect this to be 2 root 2. Okay, from our simple computation, 2 times the square root of 2 should be the answer. Okay, so let's see. But if we want the modulus, I think what is the we can use this absolute. Okay, if you want to check out this, you can always do help and then do that. Okay, absolute value. Maybe you may not know the command directly, so perhaps you could just do help and then let's say, okay, let me see if this works. I'm not so sure, but if I put absolute not found, help, let me see, help absolute. Okay, maybe that does not help. Maybe let me say, if I want to find modulus, let me see, modulus not found, help. Okay, maybe what you might do is that you just go to complex and then see, okay, yeah, maybe then you can go on maybe documentation for complex. Then you can have a few things which you can look out here. They can tell you complex numbers, and then let me see, I can click here, complex numbers, yes, then I can see absolute value and complex magnitude, abs, then angle, phase, angle, then complex, whatever, blah 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 blah, the mag is real, j real, and so on. Okay, so I know that if I want to find that, if I want to find the complex magnitude, what I'm going to do is say abs, and then we want the complex magnitude of z1 times z2. Okay, good, which should give us that, and we expected that because I think we computed it here, and then we say that it should give us 2 times square root of 2, which is 2.8284, which is exactly what we have here. So you have already seen that they told us that if we want to find, the angle here, we are simply going to do that, z1 times that, and then we get the answer. Okay, now maybe I can just show you. I know z1 is 1 plus j, 1 plus j, 1 on the x-axis, on the real part, and then 1 on the imaginary. You know that angle is just 45 degrees to the positive x-axis. Therefore, I expect this value here, if I say angle of z1, it should give me 45 degrees, but this is in pi radians. But yeah, we can convert it, because all we need to do is to get maybe answer. If I want to convert it to pi radians, what do I multiply it to degrees? I think it is 180 of pi in math is just written as that, which is 45. Okay, so yeah, it's good you can just play around with some of this and see what you get. Okay, so Euler's formula. What else with Euler's formula? Was this the text we are using? No, that one. I think we're here. Okay, so you can check out complex, and then you can work out the parts there. Okay, now we want to see the relationship between the circular and the hyperbolic functions. So we have seen the circular, we can write it as this, okay, choosing our Euler's formula. And then clearly you can see that what if the j now becomes negative j, okay, then we are going to write it as what do we write it as? Yes, if this is e j theta is cos theta plus j sin theta, then e negative j theta is simply cos theta minus j sin theta. Okay, and then what else? We can deduce that cos theta is given as this. You can see clearly that this, if maybe you call this, okay, this and that, if you add them, okay, if you add this and this, then you should be able to get this result here, because if you add them on the left hand side, you have e j theta plus this one here, which is e minus j theta, and then cos plus cos, you have 2 cos theta, and then j sin theta plus negative j sin theta is 0. So when you divide by 2, and then you get this result here. So the sign is, you just add, okay, you add, and then here you subtract. You subtract these equations here, subtract this, and then you add this. Okay, you should be able to get that result. So again, previously, of course, we didn't look through this, but for now we can take it as true that the hyperbolic cos of x is e to the x plus e minus x divided by 2, and then the hyperbolic sine is e to the x minus e to the minus x divided by 2. So if we compare these results here, if we compare this equation here, 3.112a and b, okay, with this one here and this, clearly we can see that if we are to say hyperbolic cos of j, okay, then it would be this jx minus that jx, which is the definition here of our cosine. Okay, and then clearly we can also see that if it is hyperbolic sine of x, then you just come, where's this one? Where's the hyperbolic sine of x? Yes, hyperbolic sine of x. Oh yeah, sorry, it's down here. Hyperbolic sine of, hyperbolic sine of x is given as that. Therefore, hyperbolic sine of jx, it is just like this. We put the j here, and then you have the j, and then you have the j. But we know that this is the definition of sine. This is the definition of just a minute. Okay, let me see, ejx minus ej, this, oh yeah, divide, okay, divide by 2, okay, that is, if you divide it by 2, is just the j sine theta. Okay, you can put the j here, you can put the j, and then you remove that. This is exactly what we have here. Okay, so that is the relationship which we have, or which we have deduced as the cos and its hyperbolic counterpart is the relationship is that the cosine of x equals hyperbolic cos of jx, and then the hyperbolic sine of jx is equal to just j times sine x. Okay, and then similarly, if it is this, you know the deal, you simply say this would be what? This, if you want the hyperbolic sine of that, tan of that would be the hyperbolic that, hyperbolic sine jx over hyperbolic cos jx. But we know that the hyperbolic sine that has given us j sine x, and then this one here gave us simply cos x, so that is why they write it as j tan x. Okay, also, yes, we have seen that ejx, cos jx, sorry. Okay, we know, we have already seen that cos x is given as e, okay, what is it here? E j theta plus e minus j theta. This is j theta, okay, plus e minus j theta divided by 2. Therefore, now if I want this one here, j, then I am going to multiply by the j also here, it becomes squared, and then I multiply by the j here, it becomes squared. But then we know that j squared is -1, so we have that, okay, then plus, then this one here, j squared is -1 times the negative, which will become positive over that. And we know that this is the definition. Okay, I'll make this theta, so I'm confusing notation, but we know that this is the definition of the hyperbolic cos of theta. Okay, similarly, you just use this sine jx, just do the same as we have done there. Okay, we just multiply the j times from this result here. Okay, sine, we know that sine theta is that, therefore sine j theta is going to be, we'll do that squared and then squared. Okay, and then what will it be? Then we know that j squared is -1, so you have that, and then j squared is -1 times that negative, you become a positive, divide by 2j. Okay, so yeah, this divide by 2j, which we know is simply going to be j times multiplied with sine of, hyperbolic sine of x. All right. Okay, so similarly you can also show this one here the same way by just getting this divide by that. Okay, sine, yeah, it is sine divided by cos, then you can know, we can see that it is going to be j times the hyperbolic tangent of x. Okay, so what else? Yeah, we can play around with these. For instance, if we want cos z, if we have a complex number z and then we want to find the cosine of z, then we can say it is the cos of x plus j y. Okay, and then you can use the identity that the cosine of a plus b is given as cos a cos b minus sine a sine b. And then the rest we can now we can start to substitute in here, because now cos j, okay, is going to be equal to the cos of this, okay, which stands for that, the x, and then the b, and then the x, and then this one here, which is this one. But we already know the expression for cos jy. Okay, we have seen that cos jy is the same as hyperbolic cos of y. Okay, and we also know that the sine jy is simply j times the hyperbolic sine. So the rest here is just substituting what we already know. Okay, so in similar way we can work out the rest of the examples here. Okay, in a similar way we can work out the rest of the examples here. So if you want to find the sine of 1/4 pi into 1 plus j, definitely you will use this identity, sine a cos b plus cos a sine b, and then the rest is just substitution. So we know this and this, so you have this and then you have this, but then you know this one here, what is it going to be? It is simply going to be the what, cos of 1/4 pi. Okay, and then we know this one here, not 1/4 pi, sorry, hyperbolic cos. Okay, and then we know that this one here is going to be j times the hyperbolic sine of 1/4 pi. Okay, so that is all they do here, the substitutions they make. Okay, so I'm sure you can follow through the rest of the examples and also the other identity. Okay, the other identities which are given to us, these are all familiar, I suppose, from your high school. The rest is just following and then making the appropriate substitutions. Okay, so I think we shall stop there for now, and then in the next part we shall look at the logarithm of a complex number. If there is anything that is not clear, you can always put it in the comment section. I'll be happy to respond. Alright, thank you and see you in the next video.